Hello everyone, welcome to the 24th lecture of the course Discrete-time Markov chains and Poisson processes. So in the last two lectures we solved a few problems. In today's lecture we will start with a new topic which is time reversibility. Okay, so let Xn be an irreducible Markov chain. Okay, before starting with the theorem, let me say a few words. So what is a Markov chain? We say that a process Xn is a Markov chain if given the present state, the evolution or the future evolution does not depend on the past. That's what a Markov chain is. Now, so this is something talking about the forward evolution. Now, what if we look at the backward evolution, right? So, what do I mean by that? So, suppose say you are told that you are given the states x100, x99, x98 and you are asked about x97. So, these states you are given x98, x99 and x100 you are given and you are asked that what is the probability that x97 was a certain state. So, basically you are being asked question about backward in time. So, now the question is, can you answer this question? And another question is, in order to answer that question, how much of this information is relevant? Do you need all these states x98, x99, x100 or you just need x98? Let us see. So, that's the motivation or that's the starting point. So, Markov chain definition talks about future evolution. What if we look back in time or we reverse time? Fine. So, we will start today with a theorem. Okay. So, let Xn be an irreducible Markov chain with stationary distribution. One small thing. So, you see here we are looking at 0 less than or equal to little n less than or equal to capital N. Till now we were just looking at for all n greater than or equal to 0. So, we were looking on an infinite time horizon, but here we are looking on a finite time horizon. Very soon you will see why we need that, but again nothing changes. You can look at a Markov chain on a finite time horizon, all definitions, everything remains intact, right. Here we are looking at the Markov chain on the time horizon 0 to capital N, fine. Now, define Yn to be x of capital N minus small n. So, you see that is why, because so we cannot talk about some x infinity minus something, right. So, that is why we need to look at on a finite time horizon. So, we are defining y small n to be x capital N minus n, right. Then Yn is again a Markov chain with initial distribution pi and transition probability matrix p hat, which is given by this equation. What is it? That pi j p hat ji is equal to pi I pij. So, basically it is saying that the entries of this matrix, the transition probability matrix satisfies this relation, that pi j of p hat ji equal to pi I of pij for all ij, right. So, what it says is that, like now if we go back to the question which we started with, it said that it says, so what this theorem tells you is that, like, okay, if you are looking back in time, that is again a Markov chain. That means if you are given information about x100, x99, x98 and you are asked something about x97, a probabilistic, like what is the probability that x97 is equal to I for some I in the state space, then you only need that what the 98th state is. So, again this you can think of as the current state. So, you do not need too many things in future. So, you only need x98. That is what the meaning of the statement, that Yn is again a Markov chain. Now, remember here we are the initial distribution is also important. The initial distribution is if you start with pi. So, that is also important. So, be an irreducible Markov chain with stationary distribution pi and you also start the Markov chain at pi. So, this is also important, that probability. So, x0 equal to I is pi of I for all I in S. That is also important, that the initial distribution is the stationary distribution. So, you start from the stationary distribution. So, that is also there. So, if xn is an irreducible Markov chain with initial distribution pi, where pi is also the stationary distribution, then if you define yn in this way, where yn is x capital N minus small n, then yn is again a Markov chain with initial distribution pi and transition probability matrix p hat, which is given by this relation. Moreover, yn is also irreducible and has invariant distribution pi. Fine. So, remember, so this point is important, that you are starting from the stationary distribution. Fine, that probability x0 equal to I is pi I. If the initial distribution is not pi, this theorem is not true. And again, this pi is not any initial distribution, but pi is, it is also told that pi is the stationary distribution of the Markov chain. So, here that means the stationary distribution. So, it is like, since it is irreducible, the Markov chain will have, if there exists a stationary distribution, then there will be a unique stationary distribution. So, here basically you are told that, okay, the unique stationary distribution exists and you take that as the initial distribution. If that is the setup, then if you define your yn in this way, then yn is again a Markov chain with initial distribution pi and transition probability matrix, this p hat, where p hat is given by this relation, right. Further, yn is also irreducible and has initial distribution pi. Fine. Okay. So, what this is telling you is that if you, so for a Markov chain, we know that if you are trying to predict the future evolution, you only need the current state and nothing from the past. Similarly, if you start a Markov chain from the stationary distribution, an irreducible Markov chain from the stationary distribution, and look backward in time, then that is again a Markov chain, right. So, more specifically, you have to give an example. So, if you are given the states x98, x99 and x100 and you are asked about x97, then only you need to know what x98 is. From that, you can make a probabilistic statement. So, what is the probability that, say suppose, so if I ask you what is the probability that x97 is equal to j, given that x98 was I, that is now equal to p hat I. Fine, that is the meaning of that, this is the transition probability matrix. And the Markov property means, like, in apart from this, if you are also given say x99, anyway, let me not write this again. So, again, if you are given some extra information, say x99, x100, still this probability is just this p hat ij. So, only you need to know x98 in order to say something about x97. You do not need anything more in the future like x99, x100 and so on. Fine. That is the content of this theorem, right. But remember, one important thing is you start the Markov chain from the stationary distribution. Then if you reverse it, then it is again a Markov chain with the same initial distribution, and the reversed Markov chain is also irreducible. Fine. So, remark that this chain is called the time reversal of xn, and you can easily see that from the definition, because you are looking backward in time or you are reversing time. Fine. So, this chain yn is called the time reversal of xn. Now, one more definition. Let xn be an irreducible Markov chain with transition probability matrix P and initial distribution pi, where pi is also stationary distribution. Now, you know, in this case, if you reverse the Markov chain, then it is again a Markov chain with initial distribution pi and transition probability matrix p hat. Also, this time reversed chain is irreducible and has pi as invariant distribution. Now, if for all n greater than or equal to 1, the time reversed chain Now see, now we are looking at xn, the Markov chain of infinite time horizon. But if you have to, so what is, but for the definition, what we are saying is that if for all n greater than or equal to 1, this time reversed chain also has transition probability matrix P, then xn is said to be reversible. Now, in order to define this time reverse chain, you need to just look at the Markov chain on a finite time horizon. That is why what this definition is telling you, you say a Markov chain. Now, when xn for n greater than or equal to 0 on the entire or the infinite time horizon, it is said to be reversible if for all n greater than or equal to capital 1, if you look at this reverse chain, then that is, so this first theorem tells you that, well, that will be again a Markov chain with initial distribution, that will be again an irreducible Markov chain with initial distribution pi, which will also be the stationary distribution, and the transition probability matrix will be p hat. Now the so that is for any irreducible Markov chain starting from the stationary distribution. But further, if you know that this p hat is equal to p, that means this transition probability matrix of the time reverse chain is same as the transition probability matrix of the original chain, then you say that the Markov chain is reversible, right? Okay. So again, what is the meaning of also has transition probability matrix P? That means, so you know that the reverse chain transition probability matrix is P hat. What this definition is telling is, if this P hat is equal to P, or in other words, what it means is that if P hat of ij is equal to P of ij for all ij, then you say that the original Markov chain is reversible. Fine. So, if the transition probability matrix of the reversed chain is same as the transition probability matrix of the original chain, then you say that the Markov chain is reversible. Fine. Okay. Now, we will see a couple of examples. So, first consider the Markov chain with this following transition probability matrix. Fine. Now, again it is easy to see that this Markov chain is irreducible. Any two states communicate and has unique stationary distribution this. Now, why? Because you can again check that this is a doubly stochastic matrix, and we have already seen this result. So, if the transition probability matrix is doubly stochastic and the chain is irreducible, then the unique stationary distribution is given by 1 over n, where n is the number of states. So, here the number of states is 3. So, the unique stationary distribution is given by 1 by 3, 1 by 3, 1 by 3, right. Now, if p hat satisfies this, remember we are trying to check whether this Markov chain is reversible or not. Now, what will be the transition probability matrix of the reverse chain? It will be p hat, which will satisfy this. But now, you know that, so here what is pi j? Pi j is equal to 1 by 3 for all j. So, this and this are both equal to 1 by 3, and hence they get cancelled. So, p hat will satisfy this. So, p hat of j I will be equal to p of I j, right, since pi j is same for all j. So, this will get cancelled from both sides. So, p hat will satisfy this relation, or in other words, p hat of j I should be equal to p I j. Now, if this Markov chain has to be irreducible, that means what? That means, again see, so here it says that p hat of j I equal to p I j, but I have written as p hat of I j equal to p j I, but since this is true for all I j, you can just interchange I and j. But then if this has to be time reversible, then p hat of I j should be equal to p of I j, but what this relation is telling you, this is equal to p of j I. So, this Markov chain will be reversible if p of I j is equal to p of j I for all I j. But you can clearly see, say for example, p of 1 2 is not equal to p 2 1. What is p of 1 2? P of 1 2 is basically, so you are looking at p of 1 2, right. So, first row is 1 and second column, so basically this. So, you are looking at this, that is p of 1 2 and this is p of 2, 1. You can clearly see, so 2 by 3 is not equal to 1 by 3. So, this Markov chain is not reversible, because you see, like, if it has to be reversible, then at least for this particular case it has to satisfy this condition that P of ji should be equal to P of ij for all ij, but you can see P of 1 2 is not equal to P 2 1. Similarly, you can also check, say for example, P of 0 1 not equal to P of 1 comma 0, because this is P of 0 1 and this is P of 1 comma 0. Fine. So, this Markov chain is not reversible. Fine. So, let us look at another example. Now, we consider another Markov chain with the following transition probability matrix. So, this matrix is very similar to this, but with a slight modification. Anyway, so the Markov chain has this transition probability matrix. Again, it is easy to check that the Markov chain is irreducible and has unique stationary distribution. This because again you can check that this matrix, the transition probability matrix, is doubly stochastic. Fine. Now again, thus if P hat has to satisfy this by the same calculation as before, it should be P hat of ij is equal to P of ji. But now you look at this matrix, here P of ij is equal to P of ji for all ij. So again, so if this chain has to be reversible, you need P hat of ij should be equal to P of ij, but since the stationary distribution has all components equal, this is basically equal to P of ji. So this chain will be reversible if P of ji equal to P of ij for all ij, and that is precisely true for this given transition probability matrix. So you see, this and this is same, this and this is same, this and this is same, and obviously so you only need to check this for I not equal to j, because for I equal to j that is trivially true. Fine. So here is an example of a transition probability matrix, or here is an example of a Markov chain which is reversible, right. So you see, we have seen both the examples, one of a Markov chain which is not reversible and another of a Markov chain which is reversible. Just the transition probability matrices are very similar, but with a slight difference. And so in one case it is reversible, in the other case it is not reversible. Fine. Okay. So moving forward, so that was about time reversibility. Now we will see another definition. So initially you might find, okay, from where this definition is coming, but slightly later you will see that, okay, everything is connected. So what is that definition? So let Xn be a Markov chain with transition probability matrix P, a non-negative row vector lambda, where the size of the row vector is equal to the size of the state space, and P is the transition probability matrix, are said to be in detailed balance if this condition is true. Lambda j p j I is equal to lambda I p I j for all ij. Fine. So that's the definition of detailed balance. So let Xn be a Markov chain with transition probability matrix P, a non-negative row vector lambda. Non-negative means each lambda I is greater than or equal to 0. So such a non-negative row vector and P, this transition probability matrix P, are said to be in detailed balance if this condition is true. Lambda j pji is equal to lambda I pij for all ij. Fine. So the obvious question is, why suddenly this condition? What is like what this condition is going to give us? If we investigate a little more closely, we will see that, so that's our next remark, that if lambda and p are in detailed balance, that means this condition is true, then lambda is an invariant measure for the Markov chain. Fine. And what is the proof? The proof is very simple. Now, sum over I belonging to S, lambda I pij, this is equal to this. Why? Because lambda I pij equal to lambda j pji, that's the detailed balance condition. But now, so again the summation is still over I belonging to S, but now when you are, because now look at this is pji. So when you are doing p sum over I belonging to S, you are basically summing up a row of transition probability matrix, and that is equal to 1, right? Because you are summing it over I and this is Pji. So, this you are actually summing up over the jth row. So, that sum should be equal to 1. So, and again lambda, the sum does not depend on j. So, you can even take out lambda j outside. So, this becomes equal to lambda j. So, finally, you get lambda j equal to sum over I belonging to S lambda I pi j, and this is true for all j in S. Fine. So, and this is precisely the condition for stationary measure, right. So, recall the definition of a stationary measure. It says that a row vector with non-negative entries is said to be a stationary measure if it satisfies this condition, right. So, we see that if lambda and p are in detailed balance, then lambda is an invariant measure for the Markov chain. Fine. So, you see, so in general, in order to find a stationary measure, you need to solve this set of equations given by pi p equal to pi. Now, you see this. So, again this is also a set of equations, but this is a much easier looking or simpler looking set of equations. So, in many cases you will see some examples later that calculating this detailed finding solutions to detailed balance equation is easier than finding solution to the stationarity equations. So, so this is a special case. So, if the detailed balance equations is true, or if lambda and p satisfy the detailed balance condition, then lambda is an invariant measure, right. So, if you can show that the detailed balance equation has a solution, then you can find an invariant measure. Now, if that invariant measure, if the sum of all the entries is finite, then you just divide by that sum and you can make it an invariant distribution, right. So, this is a way of finding invariant distribution, and why we are looking at this, because this way is slightly easier than finding it from the original equation set of equations, which is pi p equal to pi, which is slightly more complicated than these detailed balance equations. So, detailed balance implies stationarity. Obviously, if it is a stationary measure, it need not satisfy detailed balance equation, but if it satisfies the detailed balance equation, then it is a stationary measure. So, this detailed balance is a stronger notion. So, if it satisfies the detailed balance condition, then it is a stationary measure, or it is an invariant measure. So, and further, if you can show that if that sum of the entries, so if the sum of the entries is infinite, or if it is 0, then again it will be just an invariant measure, you cannot do much with that. But if the sum of the entries is finite, then you just divide by the sum to make it an invariant distribution, right. Because if something is an invariant measure, then if you just multiply it with a constant, it remains an invariant measure. But now, since we are dividing by the sum, it will become an invariant distribution. So, this is a way of finding invariant distribution. So, if you can find solution to the detailed balance equations, that is a way of finding invariant or stationary distribution. Fine. But why the important thing is that you will see cases where finding solution to the detailed balance equations is much simpler, because this is a much simpler looking equation as compared to the stationarity equations. Fine. Okay. So, now the question is, okay, in the first couple of slides we looked at this time reversibility, and then suddenly we moved to detailed balance equations. Okay, detailed balance equations is useful because if we can find a solution to those detailed balance equations, we can find invariant distribution or stationary distribution. But is that the only reason why we brought this stationary distribution, this detailed balance equations? Then we could have brought it when we dealt with just stationary distributions. Why did we bring it in the lecture of time reversibility? That is because these two are connected. What is the connection is given by the next theorem. So, let Xn be an irreducible Markov chain with transition probability matrix P. let pi be a positive row vector. That means pi I is strictly greater than 0 for all I in S, such that the sum is equal to 1, or fine, or in other words, it's a distribution, fine. Then the following statements are equivalent. Again, what is the meaning of the following statements are equivalent? That means the statements are if and only if. One implies the other and vice versa, fine. So, pi and p are in detailed balance, you know what that means. And the second statement is pi is stationary distribution for xn and xn is reversible. So, if you can find, so if you are given an irreducible Markov chain and if you can find a solution to the detailed balance equation, then it is not just that solution is a stationary distribution, but further the Markov chain is also reversible. Well, in this course I am not being able to give you the full justification of why reversible Markov chains are useful, but if you do any further course on Markov chains or some advanced course in Markov chains, then you will find out why reversible Markov chains are useful. I'll just make one statement like, so if you know what Markov chain Monte Carlo is, then that is one place where this reversible Markov chains plays an important role. So if you don't know what Markov chain Monte Carlo is, you don't need to bother, but just keep this thing in mind that why we are looking at reversible Markov chains, or that is because reversible Markov chains have some useful applications, but we are unable to give such applications in this course because we have some other things to do. But reversible Markov chains are important. Keep this point in mind. So we are not just studying them just like that, but we are studying them because they are actually important and has many applications in various places. One such place is Markov chain Monte Carlo, if you know what it is. If you don't know, don't bother. Fine. Anyway, so again, so what this theorem is basically telling you is that, okay, if you are given an irreducible Markov chain and if you can find a solution, again a positive solution or to the detailed balance equation. That means if you have a pi where each component or each component of that is positive, it sums up to 1, and pi and p satisfy the detailed balance equation, then it is not just true that pi is stationary. We have already seen that if the detailed balance equation has a solution, then from that you can find stationary distribution, but further the chain is also reversible. So if the detailed balance equation has a solution such that each pi I is strictly greater than 0 and they sum up to 1, then it's true that yes, one, that it is an invariant distribution or a stationary distribution, but moreover it is the Markov chain is also reversible. And this statement is not just one way, it is an if and only if statement. That means if you know that, okay, pi is a stationary distribution such that and the chain is reversible, then pi and p satisfies the detailed balance equation. So if you know that pi is an invariant distribution, and again since we are in an irreducible Markov chain, so if pi is an invariant distribution, we know that all components must be positive. So this we saw independently, that if you have an irreducible Markov chain, then and you are given a stationary measure, then either everything is 0 or everything is positive. Irreducibility is the important hypothesis. So since we are working with irreducible Markov chains, if you have a stationary distribution, then each pi I is strictly greater than 0. So if you have an irreducible Markov chain which has a stationary distribution pi and the chain is reversible, so suppose you can just show that the chain is reversible, then you can also say that this pi and the transition probability matrix P of the given Markov chain satisfy the detailed balance equation, or pi and p are in detailed balance. Fine. So, now we will see the proof of it. The proof is very simple. So, first we do 1 implies 2. So, by previous remark, pi is a stationary distribution. We have already seen this, that if pi and p are in detailed balance, then pi is a stationary distribution. Fine. Because it is a stationary measure, but now since it also sums up to 1, so it is a stationary distribution. Fine. And now we need to so this part is done, that pi is stationary distribution for xn. Now we need to show that xn is reversible. So, for time reversibility, by detailed balance condition, remember what was the detailed balance condition? Detailed balance condition was pi I, Pij was pi j, Pji. Now, we know this, what is p hat? We know that this transition probability matrix of the reversed chain yn pi will be p hat, where p hat of ji. So, basically you saw pi j, that it satisfies pi j p hat ji equal to pi I Pij, but now since we know that each pi I is strictly greater than 0, so we can bring it to the denominator. So, we have that p hat ji equal to pi I Pij over pi j, but this quantity pi I Pij, because of this, is equal to pi j Pji divided by pi j, but then pi j cancels and you get equal to Pji. So, p hat ji equal to Pji for all ij. That precisely means that p hat equal to p, or the transition probability matrix of the reverse chain is equal to the transition probability matrix of the original chain, and hence the Markov chain is reversible. Fine. So, that is 1 implies 2. Now, 2 implies 1. Now, that means you are given that pi is stationary distribution for xn and xn is reversible. Reversible means p hat equal to p. Fine. Now, we know that p hat satisfies this condition, that pi j p hat ji equal to pi I Pij. That is how you define p hat. But now, p hat equal to p, that means p hat ji should be equal to Pji. So, you get this is equal to this. Fine. Now, for all ij. So, finally, what you get is pi j Pji equal to pi I Pij for all ij, and that is precisely the detailed balance condition. So, hence pi and p are in detailed balance. So, you see the proof is very, very simple. So, if you have an irreducible Markov chain with transition probability matrix P, pi is a row vector such that of the size of the, and whose size is same as the size of the state space, and such that each component is strictly greater than 0 and it sums up to 1, then the following are equivalent. The statements are pi and p are in detailed balance, and the other statement is pi is stationary distribution and the chain is reversible. Fine. So, you see that detailed balance, not only the solution to the detailed balance equation not only just gives you stationary distribution, but also gives you reversibility of the Markov chain. Fine. Okay. So, we will finish today with an interesting example of time reversibility, or how time reversibility can be useful. Again, this is basically not about time reversibility, but about the detailed balance equation. Remember, I made this statement that you will see in most situations finding solution to detailed balance equations is simpler than finding solution to the stationary equation, provided there is a solution to the detailed balance equations, because the detailed balance equations are much simpler looking. I am not saying you will always find a solution to the detailed balance equation, but detailed balance equations are much simpler looking equations. So, you first try with that set of equations. If not, then again you will have to go to the original stationarity equation in order to find the existence of stationary distribution. Fine. Okay. So, what is the example, or what is the problem? A random king. So, you know a chessboard has various pieces. One of them is the king, the most important piece. So, king can move in any direction. So, if you have played chess, then you will know that a king can move in any directions. It can go sideways, it can go up, down, it can go in all directions, provided those directions are available. Fine. So, a random king makes each we are calling it a random king because it is as if we are saying the king, like you know a random walker, right? It goes in all possible directions with certain probabilities. Now, suppose here you have a random king makes each permissible move with equal probability. Fine. Now, if it starts in square marked 1, which is this square, how long on average will it take to return to 1? So, from 1 it starts making this random walk. The king is making this random walk. What is random walk? Like if you are in a particular square on the chessboard, you know in which possible directions the king can move. Now, the king moves in all those directions with equal probability. So, that means what? Say for example, if we just concentrate on this square 1, now from 1 it can go to 2, it can go to 3, or it can go in this direction, that is 5. Now, it will go to either of these squares with probability 1 by 3, right. So, with probability 1 by 3 it will go to 2, with probability 1 by 3 it will go to 3, and with probability 1 by 3 it will go to this 5, fine. So, that is one situation. Now, say for example, if we look at this yellow square, now you see what are the possibilities. Say for example, I am looking at the square 7. Now, it can go this way, 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 and it can go this way, right. These are all the possibilities. So, there are 5 possibilities. So, each move it will make with probability 1 by 5, fine. Similarly, if you look at a square, so you see why the reason why these squares are colored differently. So, you see this pink colored square, there are 3 possibilities. In these yellow colored squares, there are 5 possibilities. Now, if you look at a square here, now you will see there are 8 possibilities. It can go here, 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 fine. So, all possibilities are there. If it is a square in this green region, then so the probability that it will go to any of these squares is 1 by 8, right. That is the mechanism, or that is how the king will make its move, right. And you can clearly see that if let xn denote the position of the king after the nth move, then xn is a Markov chain where squares of the chessboard are the states. So, again, because where it will be in the next step only depends on where it is currently. So, it is a Markov chain. And what are the states of the Markov chain? Sorry, what are the states of the Markov then? So, there are 64 states because there are 64 squares. Let me just clean up this square. So, then xn is a Markov chain with squares of the chessboard, where squares of the chessboard are states. Now, from the pink colored squares, the king can move to 3 adjacent squares, each with probability 1 by 3. This is precisely what I explained just now. From here, it can go to 3 adjacent squares, which is this, this, and this, and the probability of going to each square is 1 by 3. Fine. From yellow colored squares, the king can move to 5 adjacent squares, each with probability 1 by 5. Again, so these squares, and these squares. There are 5 possible directions to go, and the probability of going in each of these directions is 1 by 5 each. So, that is for the yellow squares, and for green colored squares, the king can move to 8 adjacent squares, each with probability 1 by 8. So, again, if it is a square in this green region, then there are 8 possible directions to go, and it goes in each of these directions with probability 1 by 8 each. Fine. So, thus what is the transition probability matrix? It is Pij is equal to 1 by 3 if I is pink and j is adjacent to I, and I have explained what is the meaning of being adjacent to a square. Pij is equal to 1 by 5 if I is yellow and j is adjacent to I, and it is equal to 1 by 8 if I is green and j is adjacent to I. Now, you can easily check from here that since the king can move in any direction, the Markov chain is irreducible. So, starting from any square, you can go to any other square. So, the Markov chain is irreducible. Now, if I define lambda I in this way, so lambda I is equal to 3 if I is pink. So, remember, so here I am just grouping the states into 3 groups: pink colored states, green colored states, and yellow colored states. So, for if I is a pink colored state, I am defining my lambda I to be equal to 3. I am defining it to be 5 if I is yellow, and it is equal to 8 if I is green. Then it is easy to see that lambda and p satisfy the detailed balance equations for all ij. Why is that? Because again, now let us see, for if say I is pink, fine. So if I is pink, then what? Then what will be lambda I? It is 3, and what is Pij? It is 1 by 3. So this side is equal to 1. Now J again, so J can be either green, yellow or pink, but say for example J is yellow, fine. But then I have defined my lambda J, so because J is yellow, so lambda J will be 5 because of the definition, so it will be 5, and again what is Pji? Pji, so again, so here it is Pij, but does not matter. So if the starting state is yellow, it is 1 by 5, then it will be again 5 times 1 by 5, which will be again equal to 1. So both sides will be equal to 1 if I define my lambda I in this way. So the detailed balance equations are satisfied by this row vector. So for where the pink states are 3, the yellow states are 5, and the green states are 8, fine. So now since this satisfies the detailed balance equation, so now if I just, so this is a stationary measure now, so if I just divide by the sum of all lambda j's, then this will be the unique stationary distribution, because it is a Markov irreducible Markov chain. So if there is a stationary distribution, that is the unique stationary distribution, and so we have found out the solution to the detailed balance equation. So if I now just divide by the sum of all lambda j's, I will get the unique stationary distribution, right. Now remember what was the original question, that starting from 1, how long on average will it take to return to 1? So basically you are interested in starting from 1, if T1 is the first return time or the first passage time to 1, so you are interested in E1 of T1, but we know this theorem that if you are, it is, so again this is a finite state Markov chain, so it is irreducible, it has this stationary distributions, and stationary distribution and this mean return times are connected in the sense that pi I is equal to 1 over Ei Ti. So E1 of T1 should be equal to 1 over pi 1, but here what is pi 1, or here it is basically, yeah, so it should be lambda sum over j lambda j over lambda 1. Now there are 4 squares, 4 pink squares, 24 yellow squares and 36 green squares, fine. So 4 into 3 plus 24 times 5 plus 36 times 8, if you do this calculation you will see you will end up with 140, fine. So that is the answer, fine. So now just few remarks. So we started from here. Now say suppose we started from say a yellow square, say 4, then the same calculation, say if we are interested in E4 of T4, then what it will be? It will be sum over lambda j by lambda 4, right. But lambda 4, what is it? Because it is a yellow square, it will be 5. So you will see the answer will be different. Similarly, if you are looking at a green square, say for example if I look at E25 of T25, in that case you will divide by 8, right. So you see now, so starting from this pink square, the the average time it takes to come back to 1 is will be much longer, because here you are dividing it by 3, but if it is from a yellow square you are dividing it, remember lambda 4 is 5, so you are dividing it by 5, so it will be slightly less, and if it is a central square it will be even less because you are dividing it by 8. So these are some remarks, fine. But anyway, the important thing is, so here we have seen again many things. We have seen that this particular Markov chain here, the detailed balance equations has a solution. Using that we got the stationary distribution, and as soon as we have the stationary distribution we can say things about mean return times, and that is what the question was about. So you see again, initially this looks like a very difficult question to answer, but using Markov chain, this detailed balance equations, we have answered this in a much simple way, right. So you see it is a very an interesting example of Markov chains, of detailed balance equations and all those things. Fine. So, that is all. So, we will stop here today. Thank you all.